Good morning to Dr. Noor Alifah. My name is Matthias Lemada Anapita and I am from Group 11. Today, our group will be presenting about the reports and findings as well as analysis of our group project regarding the CPU scheduling using the round-robin algorithm. This is our group members for Group 11. All of the group members will take part in the video presentation. Moving on to our main objective, we want to simulate a working CPU scheduling simulation that manages the 100 synthetic processes. We also model this simulation to strictly follow the constraint, which is the 1.0 millisecond context switch penalty. Not only that, we want to analyze this performance using the three quantum values 3 millisecond, 10 millisecond, and 35 millisecond. This is to determine which of these time quantum value offer the best CPU responsiveness and CPU efficiency.
Today, I will be explaining the methodology behind our round-robin schedule simulation. First, our approach follows four clear rules. Number 1. Process enter the ready queue in FIFO order, first in, first out order. This means the first process to arrive is the first to be served, just like a real queue. Number 2. Each process runs for a fixed time quantum. No process can monopolize the CPU. Everyone gets a fair, limited slice of time. Number 3. If the quantum expired and the process is unfinished, it is re-in queue at the tail. It goes back to the end of the line to wait for its turn to ensure fairness. Number 4. Every switch adds 1.0 millisecond overhead to the global timeline. This simulates the real cost of context switching, the time it takes to save and load process states. Finally, this cycle will repeat until all processes are completed. That is all for me. Thank you.
In this section, we'll look at the core design of our simulation. First, each process is represented by a process control block (PCB) which stores essential details such as process ID, arrival time, burst time, start and finish time, turnaround time, and waiting time. Next, the ready queue is implemented using a FIFO structure with a DQ, ensuring fairness and cyclic execution for the round-robin algorithm. The timeline logic uses a global simulation time variable that tracks CPU execution and adds a 1 millisecond penalty after every context switch. These design choices ensure realistic scheduling behavior and allow precise measurement of performance metrics for different quantum sizes.
Next, I will explain the key finding from our round-robin scheduling simulation. This chart shows the relationship between time quantum size and two latency metrics such as average waiting time and average turnaround time. When the quantum size is small, at 3 milliseconds, the CPU performs frequent preemption. Each preemption causes a context switch, which adds a 1.0 millisecond overhead. As a result, processors spend more time waiting in the ready queue, while significantly increases system latency. As the quantum size increases from 3 milliseconds to 25 milliseconds, both latencies metric decrease significantly. Specifically, average waiting time decreases by 32% from 2476 milliseconds to 1681 milliseconds. Average turnaround time also decreases by 32% from 2502 milliseconds to 1707 milliseconds. In addition, the context switch overhead is reduced by 80% from 922 milliseconds to just 154 milliseconds. This happened because a larger quantum allows each process to execute longer and reduce the number of context switches. Based on this result, the best observed performance occurs at a quantum size of 25 milliseconds, where at this value the system achieves the lowest waiting and turnaround time and minimal scheduling overhead. This demonstrates that under high context switching cause a larger quantum size is more efficient for round-robin scheduling. That's all. Thank you.
Hello, I'm Annabelle. I will present the conclusion for this project. To conclude, our analysis shows that the optimal quantum size is 25 milliseconds. This value provides the lowest CPU overhead at 83.3% and the highest CPU utilization at 94.75%. Additionally, it delivers the best performance metrics with an average waiting time of 1680.59 milliseconds and average turnaround time of 1706.84 milliseconds. In summary, using a larger quantum reduces frequent context switches, thus improving the efficiency while maintaining acceptable responsiveness. That's all from us. Thank you.